To get around these, you can use things like the t-test that can use the statistical significance of a correlation. It determines whether the slope of the regression line is statistically different than 0. And certainly as you measure more points, the more confidence you have in the quality of that correlation. So rather than just quoting the correlation coefficient, you should also quote some kind of p-value that assesses whether it's a significant correlation. Now in scatter plots, you can also see another phenomenon, and this is illustrated here, which is called an outlier, a data point that just doesn't seem to belong. Now that outlier can be either a mistake, often it proves to be, maybe it's a typographical error or a data entry error, or sometimes it's actually an indication of something that's important. So outliers, depending on where you're looking at, can be both good or bad. If you see an outlier in a prediction or modeling test, then that may suggest your model is not good. As I said, outliers often indicate potential errors, simple ones that can be easily corrected. But occasionally, when you're looking at outliers for genomic or proteomic or metabolomic experiments, those actually can be something significant. They might be potentially useful markers, or they might be indicating some unusual trends that need more explanation. Now, the other thing that I mentioned about the importance of scatter plots is this ability or tendency to plot predictions versus observations. And correlations are a great way of measuring the quality of a prediction. So with different predictors, you can use things like informed parametric equations, linear regression, logistic regression, linear mixed models, machine learning, to take various parameters and predict results, and then compare those results to what's observed. That correlation that you generate is a measure of the quality of your test or your predictor. Now, the tendency is that people will develop predictions and predictors just on their training data set and won't use or assess the predictor on anything else. So it's possible to train your predictor so it works perfectly on the data you have. But when you apply that predictor to any other data that's related, you find it does very badly. So for evaluating continuous predictions, we use correlation coefficients. As I'll show you later, we can also develop predictors for predicting categories or classification. We have to use a different method to evaluate the quality of these predictions. We use sensitivity and specificity. But regardless of whether you're doing continuous value prediction or category prediction, you still have to worry about testing and validating your predictions. So testing and validation essentially makes sure that you're not using too few or too many parameters. The tendency is actually to use too many or to overfit. And this is illustrated in these images at the bottom, where we look at a data set in these yellow-orange lines, and we're plotting some phenomena, and we're trying to come up with some curve or equation or predictor that fits the data. The one in the middle, we have a perfect fit. The one on the right, we're basically overfitting. We're able to explain every noisy bit in the data. We're almost sort of connecting the dots to the lines. The one on the left is a little bit of underfitting. We're just simply trying to draw a straight line through something that actually has a bit of a curve to it. Now, making a predictor or prediction, as I said, you can use machine learning methods, statistical methods, parametric equations. But what we always have to avoid is overfitting. With computers, with software today, and with our tendency to always want to have our data fit everything perfectly, we can tend to overfit. The tendency is for people to just take the data that they've measured, develop an equation on the data that they measured, and assume that that will work for anything else. That's an example of overtraining. And the best way to prevent that overtraining is if you've got your data fitting for your data set, Well, repeat the entire experiment on a completely different data set with different subjects or individuals and see if that predictor still works. So that's the best way of confirming if it really works, if it's reproducible. Another approach is to use what's called cross-validation. I'll explain this a little later, or leave one out. A fourth method is to use permutation, which is another technique that we talked about how to distinguish empirical p-values. So the way that a predictor and the way that people should assess a prediction is to take data sets and to divide it into two groups. One will be a training set and the other will be a testing set. This is called a holdout method. In some cases you can take half or 2/3 of the data to be the training set and then half to 1/3 of the data to be the testing set. The testing is the holdout data. When you train on the training data, you can't allow it to see the test data, ever. This is a common mistake that people make. Once you've trained on the training data, then your model, your predictor, must then be applied to the test data. And you want to assess the performance. And the correlation, ideally, between the test and the train with the model should be pretty close, within about 5%. If they're vastly different, then it tells you that you've either overtrained your data or you've made some mistaken assumptions. Now, this holdout test or twofold cross-validation can be extended to something called threefold cross-validation. So in this case, if we divide our data set up into 3 different groups, we can conduct 3 rounds of testing and training on a single data set. So this is illustrated visually here, where I've taken the data set in light blue, divided it up into 3 categories. In one test, I take the 2 left portions, those are the training set, and 1/3 is the test set. I can then reverse things and take the red set, which is on the left now, and the blue set is the training, or I can divide it into 3 segments, which is shown at the bottom. So in essence, I've done 3 different tests where the reds are marked and essentially have looked at all the data and essentially assessed how well the model performs. I can go from 3-fold to 4-fold to 5-fold to 10-fold. Either way, it's a way of testing, and it's equivalent to the holdout example I mentioned before. Another way of testing and confirming that the model isn't overtrained is to do something called leave one out. So we can take a data set, train on all 99 samples and leave one out, and then repeat the process 99 times. So these are ways of ensuring, especially if we don't have an external data set, that our model, our predictor, isn't overtrained. I'm going to switch gears again and talk about the differences between clustering and correlation. So we're looking at a plot here where we've got height versus weight, and we've drawn a correlation line between the lower left and the upper right, and we can see we've got a pretty decent correlation coefficient. Now, if we take that line out and then just look at the data again, we might see something a little more interesting. Most of you will see that there's not just a line or a linear relationship between height and weight, but we'll see actually 2 different clusters. This question is it right to calculate the correlation coefficient? Well, it certainly tells us there's a relationship, but if we colored the dots according to something else that we found out, blue dots are male, the pink dots are female, that in fact there is a distinct cluster, and we can draw an ellipsoid around each of them. And so this relationship between height and weight not only reveals a linear relationship, but it also reveals a clustering phenomena. So clustering